Example 811 in section 814 on industrial loads is probably one of the most involved problems in the textbook. I kind of laugh at it. You know you're in trouble when the problem itself spans over 3 pages in your textbook, and then it has a half a page explanation at the end of it. So I debate. I'm going to go ahead and we're going to work through it. And there's so much stuff here. You could give this problem as a 1-question final exam in a first part of a machines course, and you'd have everything covered, I guarantee you. We're going to walk through it. We'll work through it together. It's important, I think, for you to see everything that you know to this point, or what you should know at this point, and so many things are brought together with this problem. It's really neat. There's always a few people in the class that get into this and they like it, and they say, wow, I want to be able to work problems like this. So here we go. This problem's got stuff from earlier courses you took a long time ago, courses that you've forgotten a lot of it, but even goes back into 131 and 133 and all sorts of stuff. But anyway, it says that I have in this figure 821, it's an industrial motor and a capacitor. Now, I will tell you up front, this is a common connection scheme for this type of a situation, because what will happen here is that this motor, large motor like this, has a lot of inductance in it, and so a lot of times what will happen in a situation like this, a large capacitor is placed in front of the motor and to improve the power factor. So it's interesting, I think, to see that as you look at this capacitor and what we know about active, reactive, and apparent power, it is returning reactive power to the system. At the same time, there's a lot of other stuff going on here throughout, in terms of power flow diagrams, power factors, all sorts of stuff. But anyway, what he says is it's a 5,000 horsepower Y-connected motor connected to a 4,000 volt line, 3-phase, 60 hertz. It has a delta connected capacitor bank. So this is representing a capacitor bank of delta connected capacitors, and we worked an example of that earlier. The motor produces an output of 3,594 horsepower at an efficiency of 93% and a power factor of 90%. So the motor, a couple of things here. The motor is rated at 5,000 horsepower, but here in our situation, it's producing an output of 3,594 horsepower. Now, one thing we know right off the bat, right, we don't do a lot of horsepower calculations. There was really only one that we did that with. So this is probably going to be something that we're going to need to convert to kilowatts to work this problem. So let's get started. He's asking basically for everything. There are A through G answers, and we're going to stumble through, we're going to work through all of these and see what we can come up with. First thing says, what is the active power absorbed by the motor? Okay, well, first thing we might want to do here is we want to take 3,594 horsepower. We want to recognize that 1 horsepower is equal to 746 watts. Okay, and we go through the calculation, or we could say, well, like he does it in terms of kilowatts, right? He says this is 0.746 kilowatts, same difference, right? Horsepower canceled out, 0.746 times 3,594. And what we end up with is the power output of this motor is 2681 kilowatts. Okay, now it's a 5,000 horsepower motor, but it is not delivering 5,000 horsepower. It's operating at less than its capacity. Okay, that's what we're saying here. All right, now that's one thing to notice. What is the active input to the motor? Okay, well, this is beautiful here. It has an efficiency of 93%. Power out, power in, 93%. So the power into this motor and the power out of the motor, we know, well, okay, we know out, right? It's 2681. And the power in is what we don't know, but we know the efficiency. So we know it's going to be 7% more of that because it's 93%. But anyway, the power in is going to be 2681 divided by 0.93. And that is going to come out to be 2883 kilowatts. Okay, pretty good. That's part A. That wasn't too bad, right? A lot of things to notice there. You know, a lot of particulars to get to that particular point. But the output is being measured some way, and so they're looking at what the output of the motor is. Okay, the power output is 3594, running at an efficiency of 93%. So it takes more power. It doesn't convert all the power to, output mechanical power available at the shaft. There's a loss inside that motor, and it's telling us that, and it's based on that efficiency of 93%. Okay, that's one letter down. We've got 6 more to go. Take a break. Part B asks for the apparent power. No, part B asks for the reactive power absorbed by the motor, but we can't get there directly, so we're going to have to back out of that. We're going to have to get back to our relationships that we have in terms of this, which says the power factor, or the cosine of the angle between the voltage and the current, is this. We know what the power factor is. It's given to us in the problem as 90%. So this is 0.9. The power that is associated, or the active power associated with this, is 2681. Okay, and then so based on the 2681, I'm sorry, that came from the efficiency. What we need to do is the input power. My bad. I'm going to get partial credit for this, right? So this is going to be 2883 divided by over S. And then S is equal to 2883 divided by 0.9. And that tells us that the apparent power is 3203. Now, what we should do now is develop a power triangle, and that will allow us to determine what Q is. So if we go out here and we put 2883, that's our active power. That's in kilowatts. Our apparent power now, we know that is 32. We'll draw that as long as I need to, because I don't have a grid on here. Nobody knows the difference, right? So S is equal to 3203, and that's in volt amps, or kVA in this case. And so now what I can do is I can calculate the reactive power. So S is squared is equal to P squared plus Q squared, or for this particular problem, I need to solve for Q. So Q squared is going to be S squared minus P squared, square root of both sides. I will get rid of, save some writing here, and I will get rid of that. I will end up with that. The S is 3203 squared minus 2883 squared, square root of that. And the Q is going to be 1395 kilovar. And that would be this guy. Okay, so we had apparent power, and then we asked or answered the question B, which says what is the reactive power absorbed by the motor? Okay, so far so good. All right, take another little break and we'll get the next one. Okay, so this is what we came up with for the motor, right? This is related to the motor. Now the next question, little tricky here. It says, what is the reactive power supplied by the transmission line? So this is going to be system specific, right? We're going to look at the system situation here. So let's clean this up a bit, and we'll look at what's already drawn here and see if we can get ahead of this and see what's going to happen. So we know that reactors or inductors, as we commonly call them, are loads for reactive power. And that's given to us here, right? And so the reactive power supplied to the motor. We already talked about the active power supplied to the motor. This is reactive power supplied back by the capacitor bank, but this looks like the whole line reactive power is predominantly capacitive. So let's see how that happens. See if you can follow this with me and understand. The Q sub C is power supplied to the system. And so normally, as you remember back to that study, we give that a negative value, and then the net or total reactive power, you know, everything combined is going to be the Q sub C plus the Q to the motor. So if I have minus 1800 from this bank plus this 1395 that I calculated earlier somewhere, or did I erase it already? Yeah, here, right, to the motor. So the difference between those two is 405. Now, since the capacitive part of this is larger, it's going to stay a negative. And what that means is that the reactive power is actually being returned to the source. This is not a common situation, but it says this is an unusual situation because reactive power is being returned to the line. In most cases, the capacitor bank furnishes no more than Q sub M kilovars of reactive power. So most of the time, you don't return to the system more than the load needs, which is in this situation. But I think it's good, you know, to explore that happening. Okay, take another break. We'll do part D. Part D asks us to determine the active power supplied by the line. Okay, the active power supplied by the line is only that which is going to the motor, and we have discovered that that was 2883. The motor isn't 100% efficient, we know that. So ultimately the output is less than the input, but it's still 93% efficient. But anyway, what we're talking about is line supplied active power. So if we try to determine the line apparent power, it will be the active power of the line plus the reactive power of the line. And we know both of those numbers. We've calculated both of them. 2883 squared plus minus 405 squared. And so the total reactive power at the line is 2,911 kilovolt amps. That gives us part D. All right, kind of interesting, right? We did a power triangle related to the motor. We did a power triangle related to the line, and worked both of those things out. That's part D. Take a break, we'll do E. And when I say take a break, go back and make sure you understand this before you go into the next part. Part E is asking us for transmission line current. Remember that in a three-phase system, the apparent power is the square root of 3 times E times I. Now we can solve this for I, and I is going to be the apparent line power divided by square root of 3 times E. And again, this is line voltage that we're dealing with. And so this is 2911 kVA. And this is square root of 3 times 4,000. And multiplying this, dividing, we end up with 420 amps is the transmission line current. We could throw that in there somewhere. And those are very large currents, and that's the kind of stuff that you deal with when you deal with a motor. Okay, take a break, and now we'll look at F. Okay, for F, it's saying what is the motor line current? Again, we know what the, let's see, did I erase it? No, I still have it. The apparent, let's work off the motor here. The motor line current, I have the values written down for everything, I think. Do I have this 2883? Let me write that in here. 2883. Okay, now let me erase this and we'll do this. And now this is going to cause you great discomfort, but hang in here. We'll try to figure out why this is this way. The motor line current, three-phase motor, square root of 3 times E times I, line current, and line voltage. Motor line current, I, is going to be S divided by a square root of 3 times E. Now, remember from here that the apparent power for the motor was 3203 kVA. Divided by square root of 3 times E. And if I come out with that, the motor line current comes out to be 462 amps. Okay, you say, well, wait a minute, the line current was, the transmission line current was 420 and the motor line current is 462. Okay, the capacitor, think about how its direction is and it's returning. Okay, so that's a clue as to why that could be that way. All right, now the next of these actually is pretty straightforward. I'm not even gonna, we won't even take a, well, let's take a break. I'm gonna break that so you can take time to make sure that you understand it. And we're almost finished with this thing. Now I'll go through and do an edit on this in a minute and take that part out. So now the last thing is determine the phase angle between the motor current and the line current. So I can calculate the line current, or line to neutral, is going to be 4,000, which is the line, divided by square root of 3. So that comes out to be 2309 volts. The phase angle between the motor current and the line to neutral voltage, cosine of the angle, equals the power factor, which is 0.9. Inverse cosine tells me that that angle is going to be 25.8 degrees. And so the motor current lags 25.8 degrees behind the voltage. And then he's saying the line current drawn by the capacitor bank, is given as, well, it would be Q sub C equals, square root of 3 times I times E again, right? And that would come out to be, well, we already knew what this was, right? This was 1800 kVAR divided by square root of 3 times line voltage 4,000, which gives us 260 amps. Now, that's a lot of stuff. What would the phasor diagram look like for that? And what does this problem look like solved? Okay, well, let's fast forward here to this, and we'll put all this in here and see if it makes sense to you. Okay, so here is the 2390 voltage here, and that was associated, if you'll remember back somewhere. Do I still have it anywhere? Well, I've sort of torn all this apart, haven't it? But that goes back to the part of the problem initially, where we were calculating that line to neutral voltage based on a 4,000 volt line voltage. And then for the motor, we know that the motor draws 462 amps, and it had a power factor of 90%. And so that is showing that angle there, okay? So here's the current, and it lags the voltage by 25.8 degrees. Okay, now beyond that, what else do we know? Okay, the capacitive current, it is going to lead that line voltage, or the 2390, by 90 degrees, since it's purely capacitive. Now, the last thing here is, he says, where should the phasor current I sub C be located on the phasor diagram? The capacitors are connected in delta. We can assume a Y connection for the motor. There's that assumption. This can create unnecessary phase angle complications if we try to follow the actual currents inside the capacitor bank. The solution is to recognize that if the capacitors were connected in Y while generating the same reactive power, the line current of 260 amps would lead the line to neutral voltage by 90 degrees. This is the correct position for the phasor I sub C, no matter how the capacitor bank is connected internally, because of that, current leads voltage by 90 degrees. The phase angle between the transmission line and the current, okay, is this. And how do we come up with that? Well, that's just going to be active over apparent to the line. Active is 2883 divided by 2911 for the apparent line. Comes out to be 0.099, which comes out to be a small angle of 8 degrees, which we're seeing there. Okay? What do you think? A lot of stuff there, right? A lot of things to digest and try to understand. The line current, 420 amps, leads by 8 degrees because the kVAR supplied by the capacitor bank exceed the kVAR absorbed by the motor. The phasor diagram for one phase is shown. So you could reproduce this. You could put this line voltage, 120 degrees and do all this stuff again for each phase. He says, I want to emphasize the importance of assuming a Y connection, irrespective of the actual connection. By assuming Y, all the circuit elements are simpler and easier to understand. As a final remark, the reader has no doubt noticed that the solution of a three-phase problem involves active, reactive, and apparent power. The impedance values of the devices, such as the resistors, motors, and capacitors, seldom appear on the nameplate. This is to be expected because most industrial loads involve electric motors, furnaces, lights, and so on, which are seldom described in terms of reactance or resistance. They are usually represented as devices that draw a given amount of power at a given power factor. That is a big mind shift for us. As up to this point, we've focused on tracing currents, going through elements, but let me say that one more time. The impedance values of devices such as resistors, motors, capacitors seldom appear on a nameplate. This is to be expected because most industrial loads that involve motors, furnaces, lights, and so on, which are seldom described in terms of resistance or reactance. They're represented by devices that draw a given amount of power at a given power factor. And we can figure out from that information what's going on. The situation is somewhat different in the case of three-phase transmission lines. We can define resistance and reactance because the parameters are fixed. The same remark applies to equivalent circuits describing the behavior of individual machines, such as induction motors and synchronous machines. Okay, now that's getting way down the road. And like when we go into synchronous generators, for instance, we break this down and we actually do look inside of that and the reactances and resistances. But again, that's specific to a particular type of device. And what he's talking about is loads in general. So he says, in conclusion, the solution of three-phase circuits may involve either active and reactive or RLC elements, and sometimes both. Okay, so you can see this can get pretty involved, but at the same time, the math that's involved is pretty straightforward and simple through there. If you're still here after all of that, I commend you, and I hope you picked something out of this as we went through it.